This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
I'll go one step further on the advertisement and leave the screen capture on for the beginning of the recording, so it's even locked in to the beginning of the lecture capture. For those who may have missed the lecture captured on the screen right now, are the details for an event being held tonight, is it? It's tonight. So if for some reason you're listening today to the lecture, this is what you should be doing tonight rather than listening to the lecture. Just waiting for everything to load up here. There we go. Okay. Good. Let's get into it. Okay, so yesterday was all about introducing the idea of enthalpy, and we used, as we developed the idea, we were using a closed system boundary, and we were using a constant pressure process. And the important thing about the derivation was that we were doing those things just for the derivation. We were doing them just to make our life easy as we built up a brand new concept. And once we built up the brand new concept of enthalpy, we are now free to use it. So today is about when do I use it? When do I care about worrying about the energy contained in the boundary work, rather than just solving a problem for the temperature of my system connecting to my internal energy. So we're interested in steady flow problems. We built up the non-flow energy equations for the closed system boundary, and those ones we solved with internal energy, which is to say that if it was a steam problem or a vapor problem, we would look up the internal energy, the U column of the tables, and if it was an ideal gas problem, we would be using CV delta T to solve the problem. On a steady flow problem, I'm just going to spoilers, on a steady flow problem, if it was a steam problem, we would be looking up enthalpy in the steam tables, and if it were an ideal gas problem, we'd be using CP delta T to evaluate our delta H. So that was the point of yesterday, and today we're going to establish that as real, and then do one worked example on a turbine, which is about as close to an actual thermodynamic question as you get. So we need to first have a look at the difference between, remember I said as we were developing this idea of the closed boundary system, it let us get rid of all the other types of work and just deal with what I was referring to as boundary work, which is the pressure volume work. So we want to separate that out from the most common work type that we'll put into or get out of most of our thermodynamic machines, which is shaft work, which is either the work I put into the system or the work I'm getting out of the system, usually through a shaft. So this is particularly important for compressors and for turbines. And if you're doing if your system boundary of an engine were to include the output shaft of the engine, then you would also have shaft work coming out of the engine system boundary. Reciprocating engine. So let's get us an arbitrary system boundary. This device isn't anything. It's just got ins and outs and a boundary, and one of the boundaries is a wall, and one of the other boundaries are open. So let's have a look at it. The black line is the system boundary, and it doesn't really matter what shape it is for the purposes of this calculation. At each end, I've got an open boundary, an inlet, and an outlet. So this is not closed, this is open, which means that mass can transfer across my system boundary. I have some heat transfer. I'm not making any assumptions about this. I'm not making any assumptions that it's adiabatic or insulated. And I also have some work out, and the work is coming out through a shaft. And so I'm just tagging all of those different elements to say we've now got basically one of everything that we had originally written down in our energy balance equation in the first law. I've also given a delta Z, so I've got a change in potential energy, and I've given a velocity. So this big V is not volume, it's velocity. I've given a velocity, which means I've also got a delta KE. I've got a change in kinetic energy. So now now I'm bringing everything back in. We spent a couple of weeks of trying to cross terms off to make our life easy. This one I'm just putting it all in, but I'm also doing it on a flow basis, which means that I have the concept of a rate of mass transfer through the system, an m dot, so kilograms per second. And if I've got a per second element to my problem, then instead of doing energy, we're now dealing with power. So at the total system description, I'm now interested in Q dot and W dot. W dot is power, it's kilojoules per second, or watts, or kilowatts. And Q dot is a heat transfer rate, so it'll also be kilojoules per second, or kilowatts. So that's all the different bits of the device, and we're going to now play around with those pieces. In this flowing device, the most important thing that we're going to try to keep track of is that if I have all the information about the state at point 1 and the state at point 2, my thermodynamic job, is to evaluate what energy change occurred going from 1 to 2. And so I'm going to use all the tools I've got to try to work that out. And our new trick, which is what I've been alluding to with this whole building up of the enthalpy concept and the pressure and volume idea, our new trick is that we've been able to work out that if I've got two things known at a point, I've got all the properties. So imagine I've got two things known at point 1 and two things known at point 2. I can tell you everything about the state here and the state here. But in this flowing exercise, I'm also pushing some, let's call it air. Let's imagine it's air. It could be anything. Could be water, could be mercury. But I'm pushing some air into the system, and at the other end, some air is being let out. There is an energy associated with how hard it was to push some air, because that was some force exerted over a distance, and there is the opposite of that, so some energy released, or a decrease in my system energy as fluid emerges out the other side. So the enthalpy tool is the one we're going to use to help us keep track of those changes, those energy changes. On screen is effectively everything I've just said verbally. And we put it on screen so that if you don't follow my words or I speak too quickly, you can read it over my shoulder. The most important thing to keep track of, which is that last sentence, and this will come up to haunt you. You'll ignore it now, and that's okay because I'm just teaching you stuff and you're listening and you haven't had to solve a problem with it yet. But later on, these ideas come up again, and so I'm just going to wave my hand and say pay attention at this point. The work that comes out of the system, the shaft work that comes out of the system, is not all the work that's been done, either to or by the system. So this idea that it took some effort to push the air in and it released some effort, some work as the air came out, is part of the system work. It's just that we play with it in a different way. We shift it from this side of the equation, the Q minus W, over to this side of the equation, which is the delta E side of the equation. So we don't lose track of that work, we just put it somewhere else to make our equations easier. We use the continuity equation this time, and whenever you use the continuity equation, which is the conservation of mass equation, it always looks like the most trivial equation you could ever use, but if you didn't have it, you couldn't solve the rest of the problem. In this form, so in the continuity equation for the closed system boundary, you have mass 1 is mass 2 because I can't transfer mass across the system boundary. And this guy, mass is crossing across the system boundary all the time. And so to make our early life easy, we deal with steady flow problems, which is to say that the mass flow rate is constant. The m dot in is equal to the m dot out. It's one of our early simplifying assumptions to allow us to quickly solve this problem. If the m dot in and the m dot out were different, then you wouldn't have a steady state, you would have a rate of change. So your delta E term would have a rate to it, which is to say the system would be building up energy or losing energy over time. If I have a steady state system, the rate of change of energy inside the system is constant. So my delta E dot, so I've got a Q dot and a W dot, my delta E dot is 0. The rate of change is 0. So that also adds an extra ease to solving the problem. So let's take a look at, with that arbitrary system that we built up, let's take a look at some of the quantities. I've got mass flow coming in, and it comes in at some differential. So in an instant of time, we're going to start with our differential quantities so that we can say them as the infinitesimal bit in, the infinitesimal bit out, the infinitesimal change. The infinitesimal bit in a unit of time is connected to the velocity of the gas flow. So those big V's there are velocity. So in a flash, due to the velocity over an area with a certain density, I have my kilograms in. So if I follow a meters per second and a kilogram, the meters squared from my area, and I've got the kilograms per cubic meter density, all those meter, the meter 3 and the meter 2 and the meter 1 all cancel out, and I'm left with a kilogram term. So my little unit mass in kilograms, rho velocity area, and the same coming out. Since it's a steady flow, they're the same. This means that through area, I could relate velocity. If I knew the area ratios, it's my continuity equation that lets me solve the problem of how fast, what's the change in velocity from 1 to 2. So whereas in the closed volume system, the continuity equation wasn't much magic to it, in that there was just one point. The one example we looked at where we did use the continuity equation was to say I had mass in a tank and mass in a tank, and afterwards I had the same amount of mass. It wasn't particularly magic maths. This one says with constant mass flow, I can relate the velocities at the inlet and the outlet due to their area ratio, or their density ratio, which is to say if the temperatures have changed, the velocity will change. So if I've not changed the areas, but I've heated up the gas, it's occupying more space, it's going to want to push faster out of the exit. You with me? I've got there's a few little light bulbs popping around, which is nice to see. It's particularly at 9 o'clock in the morning. So the continuity equation for a flow problem gets expressed as rho velocity area equals rho velocity area. You could do that rho as a specific volume. So you could do that velocity over specific volume area. It's just easier not to have to write a fraction line. So rho velocity area is an easy way to write the continuity equation. So that's our continuity equation for a steady flow problem. And we only allowed to use that when it's a steady flow problem. That's defined by my dm1 equals my dm2. So we're going to go on to deriving the steady flow energy equation. And I am a huge fan of knowing where you're heading. Whenever someone starts to go, I'm going to derive a thing, I don't like guessing where we're going by the end. So the steady flow version of the equation, this guy here, q dot minus w dot is dm delta h half v squared gz. So my mass flow rate, actually that should be an m dot, yeah? Oh, so dm. Yeah, I'm okay. The thing to note about the steady flow equation is enthalpy. Our non-flow energy equation looked identical except that it said internal energy there. So that's the point of the next derivation is to get us there. So, on the basis of a steady flow, which means that the total energy stored in the mass entering and leaving is the sum of the internal energy, kinetic energy, and potential energy, we're going to begin with energy 1 and energy 2 as dm internal energy, kinetic energy, potential energy. And here's a little trick. The way I'm going to keep track of those energies coming in and coming out. Remember, I knew I had a velocity acting over a unit of time, over an area. I also have the pressure that's going on and the area that's acting over. Previously, we've played a game with pressure and area and dx to go into pressure times volume. We're going to do a similar kind of game here to make sure that we're doing these things in terms of properties, which is to say P and specific volume, rather than P and area. So area is not a property. So I'm going to play a little game here to make sure that I can express the energy contained coming in, not by the area that it pushed through, but by its pressure and specific volume. That's the objective of this of the next sort of slide and a half. It's a funny thing, the rambling I do now compared to the rambling I used to do a couple of years ago and the rambling I used to do when I was trying to learn the subject in the first place come from a frame of mind of when you see a derivation, the first time you see it, you're trying to work out how did that maths work. I don't understand how you got from this step to this step, but how did you get that substitution? The point of view of imagine you were in charge of the derivation the first time it had ever been done, where do you go? If you're just reading someone's derivation, you don't build up the skill set to be thinking, what are my tools for deriving a more useful equation? Why would I derive a more useful equation? And what's my goal? Why is it that I'm trying to get from this thing that looks like an equation to another thing that looks like an equation? In thermo, our derivations are to take us from statements of the physical system to a property analysis where we can actually put numbers on the quantities that are not connected necessarily to the geometry of the system. So if I tell you that the force acting on the system is pressure times area, then I need to know the geometry of the system. I don't have a generic analysis. So the exercise that's going on here is, let's go from what we know to the generic in terms of properties. Now, this property thing is a big deal in thermo. So we go into the system at v dt. So velocity dt. Over a little infinitesimal unit of time, there's been a velocity, which is to say a meter per second. And that flows, that energy is called flow work or boundary work. And so it's given by rho area velocity dt is equal to, pressure area velocity dt is equal to pressure specific volume, dm. Because those guys are slightly different terms, I was in the habit of scribbling that down and showing that the units work out. So I'm going to try that now, if my computer will respond to me. Or I could load it up after class. It's nice to be able to teach with some sense of flow and control over your world. Sometimes they take that away from you. I'm going to put up a scan of my handwriting after class that contains evidence that these terms equal these terms. And the reason I'm going to do that is this differential is a differential in terms of time. This infinitesimal thing is an infinitesimal thing in terms of time. This guy doesn't look like it's got any time in it. And so it's just nice to convince yourself that we are dealing absolutely with the same units and that those units represent energy. So work we're representing in kilojoules or Newton meters, and it's nice to just know that whatever it is that's going on there is real and legitimate. No, the system's just not responding, which is going to be challenging when it comes time to do the work example. So we'll try to, no, we'll get there. And this is the second time this has happened in this lecture theatre. That will become a frustrating thing for the rest of the semester. Okay, so if that's on the way in, I've got a negative sign there. Why do I have a negative sign there? So why do I have a negative sign there?
Because it's work done by the system.
Work done by or work done to?
To the system.
Work done to the system. So my convention was work that comes out of the system is positive. So pushing in was work done into the system, and popping out the other side is work coming out of the system. So that's got the positive there. So the total work done by the system, I've got to include the two boundary works. So these are the two that I've just been deriving here, 1, 2, and the shaft work over a unit time. So the shaft power, I've written it as shaft power, dt, and the shaft power it will be kilojoules per second times a unit of seconds, so it ends up being kilojoules. So this is now the work done. And I've got my little dm and I've got my little dm in here. And I'm in the habit of writing these equations in specific terms, which is say per kilogram. And when I divide through by my dm's, this guy makes sense if I've told you the shaft power. If I divide through by dm's, I get a little w. These are already, these dm's pop off. And I get nice equations. And when I say nice in a thermodynamic sense, I mean nice in that if I know the states at 1 and 2, I can solve this problem. Which is a little piece of magic. It's a deceptively simple piece of magic. So, if the first law is net heat transfer in minus net work done by equals change in energy of the stored system, and we have a steady flow problem, let's work our way through these next couple of steps. The delta E, E2 minus E1, I'm still working on a delta mass times delta energy. So, some little bit of mass times the specific change in energy is my delta E. And so we're going to plug all of this is now the exercise of putting them all in the same equation. So the power, the heat transfer power, the shaft work power, I should walk this way. The heat transfer power, the shaft work power, the boundary work out, the boundary work in, so the delta boundary work is equal to the little bit of mass in that moment, in that second, in that fraction of time, times the delta E of the problem. And this is where we bring enthalpy in. Over this side, if I've got my boundary work, it looks like something I don't really have control over. And it's got dm terms, which is also handy. If I take the dm terms over to this side, where I've got my other dm terms, I've now got dm PV. I can get that dm out my PVs go into the bracket. So rather than me waving like this to you, because you might not see it, if I get these guys over here, I can factor out the DM and I can bring the PV terms inside, and I've already decided that I'm perfectly content with the definition of enthalpy, which is to say that my PV terms can add up with my U and say that I can express this flow equation in terms of enthalpy. Why would I do that? Why would I do that? Importantly, why would I harp on about it for a lecture and a half? When it comes your time to pick your tools off the shelf, there's an exercise you go through. There's a set of divisions in every question of, is it a vapor question or an ideal gas question? That's one division, because it tells you, am I looking at my properties on a table, or am I using CV delta T and PV delta T, CV delta T and CP delta T? There's also the what type of problem am I solving, what type of energy problem am I solving? I'm solving closed flow or open flow, closed flow or steady flow. Closed flow, internal energy, or CV delta T. Open system, steady flow, enthalpy, or CP delta T, depending on whether it's vapor or an ideal gas. There's a couple of other divisions that we'll encounter along the way, and they're your job to keep track of, and your job to be in charge of which tools are you picking off the shelf. It's also the bit where you get marked on. Which tool you chose indicates your depth of knowledge and understanding of your thermodynamics, which is why more marks are allocated to the selecting of the correct approach to solve the problem than there are to the answer you get at the end. The job you have in this subject is learning which tools to pick when. The maths actually really isn't that hard. The only tricky maths I've seen in introductory thermo is the integral of 1 on x. Which is not to say that the maths doesn't get hard, but we start off with easy maths, but a lot of choices to make, which reflects a lot of understanding. So, common steady flow devices. Let's get some up. Very often we have adiabatic steady flow devices, or close enough to adiabatic for our purposes. So the turbines and compressors are our most common steady flow devices in terms of work in or work out devices. Nozzles and diffusers are steady flow devices, but I'm not trying to extract work out of them or put work into them. I'm just trying to change velocities. So often, when we've got an adiabatic and steady flow, then we actually get quite easy, we get extra simplifications into the problem. Also, it's quite common for during the analysis for the potential energy change to be negligible. So I do this because imagine I'm doing an aircraft gas turbine engine. It has significant potential energy, but during the analysis of the combustion process of the gas passing through, I'm not really changing my potential energy from start to finish. This thing is flying really fast. Different sections of the gas turbine, but as it's flying through air, it may be relevant to me to work out kinetic energy change or not. The turbine, the compressor, usually not. Now, if you have information on the flow velocities, you can actually establish that for yourself. You will see that the delta KE term is of order joules, whereas the delta work terms are of order kilojoules. So if I'm off by 1,000, there are terms I can neglect. So when we say that things are negligible, we're not saying they're zero. We're saying that I just don't care for this problem right now here. So most or many steady flow problems are also adiabatic with no kinetic energy and no potential energy change, which means that I'm just getting work equals delta H. So I'll do that last jump again. If I had Q minus W equals change in internal energy, and my change in internal energy was represented by H and PE and KE, and the PE and KE are gone, I've just got H. And on this side, if I don't have any Q because I'm adiabatic, I've got work equals work. Work was hard to measure. Temperature, pressure, relatively easy to measure. So I have some tools where I can evaluate my work, or I know that I've built I know that I want to build, say, a 600 megawatt gas turbine. I can tell you what job it needs to do. I can say this gas turbine, to be 600 megawatts, needs a certain mass flow and a certain delta T, because delta T is like my delta H, which is my change in energy. So either I could have a huge, to get 600 megawatts, either I could have a huge delta H and a little mass flow, or a massive mass flow and a little delta H. So now I have system design choices. For the output I want to design for, if I assume adiabatic, steady flow, kinetic potential energy is changed, now I have these really nice tools that actually let me work it out, which is also to say, how hot did it need to get? So if enthalpy is connected to hot, that's one part of it, that's the U part of it, and what pressure do I need to get to? So a turbine's job is to unleash work from high energy. I probably can't get any hotter than burning flames. So imagine I come in with burning flame temperatures, I can't get really any colder than the outside world. So now I've got limits to my system, but those don't tell me anything about the pressure. And that's my other way that I can get energy out, is to take a high pressure to a low pressure. And I go, great, so to get my 600 megawatts, I want to go, I've got this temperature, but I need to go from a high pressure to low pressure. How do I get to the high pressure? Well, high pressure didn't happen by magic. I better squeeze something really, really hard, so now I need a compressor to get my high pressure, so that when I put my fuel in, not only can I get the temperature drop, but I can get the pressure drop. So now these little tools that we've been slowly building up, these little games we've been slowly building up, begin to connect one by one into a toolbox that are actual real engineering toolboxes. Because then you get the choice of, okay, mass flow rate, if I don't have access to the delta T and the delta P that I want, it's in M dot. So to get 600 megawatts, I need whatever M dot. Imagine whatever M dot to get the 600 megawatts is so much that I end up 3 times the speed of sound on my mass flow, and my whole system explodes because of the sonic booms throughout the system. Like, okay, well maybe I'm also limited on my mass flow. So if I'm limited on my mass flow and my pressure and my temperature, I can't build my 600 megawatt system. Maybe I need 300 megawatt systems. Now I'm designing a different system, I'm showing a different cost, but I'm doing it because I've worked out my thermodynamics. I've used what look like on paper relatively simple tools to solve very, very, very real problems, which is what draws me to this subject. I go on a rant, I go blah, 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 and I end up tapping on to say, yep, that's exactly what I was just trying to tell you. So I get that my power equals m dot delta H. Usually I have things, pipe flows tend to have negligible heat transfer as well, and never any shaft work. Now that's interesting. A lot of flows go through pipes. In fact, it's kind of the definition of what a pipe's job is. So if they're generally well insulated pipes, and there's no heat transfer, so if they're insulated, there's no heat transfer, and it's a steady flow problem, and there's no work done in or out because it's a pipe, nothing sticking in and nothing sticking out, then what I have is delta H equals 0. If Q and W have gone, I've got delta H equals 0. So I have a way to evaluate what energy losses happened over my pipe. That will become useful when you get into fluids. But he won't use the same words. But you'll have it in your mind that there is an idea of energy loss in a pipe that can be represented by enthalpy, that can be represented by temperature and pressure and specific volume. But a pipe also has a velocity term. So I don't just magic away my enthalpy, I turn it into another form of energy. If I had no way to transfer energy or pressure and there's nothing going on, this is an ideal pipe, I don't have friction yet. Really, the only thing I've got to do is transfer heat and pressure energy into velocity or vice versa. That's a nozzle or a diffuser. This is where I would love to have my document camera available to me, and I don't. So that's okay, we shall power on and do this on the board, because that's the only option I've got. You're in class and we've got another 20 minutes, and so you deserve to be taught. What it means is that the lecture capture doesn't catch that, but the work solution is fully written down, already available in LMS. And I will also see if I can dig back into last year's archives of the lecture capture and get the moment of me scribbling it down on the doc-cam, because there is benefit. If you're trying to review this thing before the exam, there is benefit to seeing it sort of evolve with someone talking at you. Before we jump up onto the whiteboard, as excited as I am to use a whiteboard, you may notice this about me. Let's begin by having a look at the problem. Now you said red you can't see very well, green you probably can't see very well, so I'll just stick with black. I'm going to tap forward, it's just the one problem. We've got nitrogen in a compressor, and I'm going to give a whole bunch of thermo code words. My thermo code words are steady state, steady flow, adiabatic, and the code word of nitrogen. Why is nitrogen a code word? Oh, come now. What is that? I heard somewhere around here. Actually, the answer.
Ideal gas. It's not ideal gas.
It's an ideal gas. Why is it an ideal gas? That's okay. Because we're in class, I'm happy if you're not sure, because it's a great time to be not sure. But you started on a good path. You said air is an ideal gas. Why is air an ideal gas? Now, everyone else is getting off easy here because he's the only person answering. If anyone else knows why air is an ideal gas.
Pressure, temperature, light.
Because it looks like it should be an ideal gas, because my rule of thumb, which in the first week, when we were starting to talk about ideal gas, was if you are familiar with it, it's not the scientific truth, it's the instinct. If you are familiar with it as a gas in your normal world, it's probably an ideal gas. Air, if you're familiar with this is as opposed to a vapor. You're not accustomed to air condensing into droplets in your normal world, which means we're far away from the saturation curve of air, and air is mostly nitrogen, 80% nitrogen-ish. So nitrogen, oxygen, you are accustomed to knowing are far away from condensing into liquids. The scientific way of expressing that is that they are far away from their saturation properties, and far away from their critical point. What other code words do we have in here? Let's see if we can find any other code words. I'm not sure if there are any. We've got a mass flow rate, we've got a temperature 1, a temperature 2, a pressure 1, and we want to know the work done on the nitrogen. Why is it work done on the nitrogen, not work done by the nitrogen? That's a good answer. I'm squeezing it. I'm compressing it. It's not going to get smaller by itself. I need to put an amount of energy in to the system to squeeze it. If I let go of a squeezed thing, it will expand. So I don't need to put any energy in to allow it to expand. But when I want to do things in not the normal direction, I have to put energy in. Okay, and I've got an answer up there. So let's see if we can work it out. Now, I can't even turn the screen off to hide from you my work solutions while I scribble from them. It's lucky I brought my computer. Awesome. Sometimes technology works for me. Now you'd think by now I shouldn't need to look at my notes. I look at my notes to make sure I don't make a dumb error in the middle of trying to show you something straightforward. I harped on quite a bit on Friday about the way to structure a problem. What were some of the things I said you should do before you begin solving the problem? Diagram and
Data assumptions.
diagram, data, assumptions. I had 5 things. Diagram data assumptions.
Goal.
Hmm?
Goal.
Goal is a very important one. Write down what you're solving for
Equations.
and what principles you're going to use to solve it. So the assumptions are not the equations I'm going to solve it. The assumptions are the way I'm going to make the equation simpler. So it's possible not to write down any assumptions, and if you make the equation simpler, you can make a little note, or it's possible not to write down any assumptions and solve every term, but realize that some of the terms are zero. So you get better and better at writing down easy simplifying assumptions. And some of the assumptions, now there's a funny thing, people get afraid of writing down assumptions in case you'll be judged for they're wrong. It's a list of stuff that made your life easier. So if you're missing ones, if you're missing assumptions and I see you do something, in the beginning I'll probably just make a note saying, by the way, that was an assumption. If you put down everything you can ever imagine, the only time that they become wrong is if they're contradictory. If you're listing everything you know, so the reason I'm saying all of this is that there's stuff in the question, there's stuff that's handed to you, which are actually the simplifying assumption. They've already told you some of the simplifying assumptions or some of the guiding assumptions. So let's put all this stuff down. We wanted, you know what, I don't need to carry this around to draw a picture of the compressor. Hopefully I don't by now. Our standard compressor diagram is a thing that gets smaller as I go from left to right. I also have a tendency to draw the outlet like that, and the inlet like that. And I have a habit of putting my shaft here, and I put the notation, I put the S notation to show that it's shaft work, and I'll label this as 1, and I'll label this as 2, and I've been told it's an adiabatic compressor, so I'll put my little secret notation of insulation, imagining I'm wrapping this whole thing up in cotton wool or a blanket. And inside I'll just make a little note that this is nitrogen. And I'll also, just in case I'm not sure that people understand my picture, I'll also write down it's a compressor. I'm going to do that in case I panicked in the middle of the exam and I drew it back to front. But I want to make sure that you know that I read the question. I'll just double check. Did I draw it back to front? I have a habit of going from left to right in my flows, and going from left to right I get smaller, which should be squeezing. And I say given, so this is my data, and I'll try to list out I'll try to list what I've got in terms of state 1 and state 2. At state 1, I've got P1 equals 1 megapascal. I'm going to write the data down exactly as it was given to me. I'll say that T1 equals 25 degrees C. So I'm not writing down my temperature in Kelvin just there. I am just copying the data from the paper into my book. And I'm saying my T2 equals 125 degrees C. And I'm going to say that M dot equals 0.2 kilograms per second. That's basically all the info I've been given. Block out in space. Now, thank you. If I had have solved that problem with 1 megapascal and the question asked for 0.1 megapascal, I lose 1 mark, not 10 marks. Because it's absolutely clear where I scribbled down an error, provided that the rest is solved with ideal gas law, steady flow energy equations, first law, continuity, and with sensible assumptions, provided I demonstrate my thermodynamic skill set and tool choice is correct. I've only lost a little bit for transcription, which is to say scribbling down stuff wrong. But yes, it was 0.1. Thank you. This is my way of saying, hey, look what I deliberately did. Okay. Over here, I'm going to put down assumptions. So you'll note you'll note that when I'm doing work examples, I really take my time over it because I sit there waving my hands and trying to explain everything I'm writing down on paper. That's because we haven't had much chance to practice this stuff. You get your one tutorial a week, you get a little bit of work time in lecture, and then the rest is kind of on your shoulders to go and practice. So I take my time setting out the problem because this setting out tends to be new for people, and getting into the habit of this being, of course I'm going to set my thermo problem out like this, it doesn't come by instinct. So I really do drag my feet before I get to an analysis. Because you've seen that question on paper, you're like, oh, that looks like an enthalpy problem. Oh, I've got temperatures. I could probably solve that. All I need is pressure. Can I work out pressure? I don't know yet. Maybe I can just jump into writing down enthalpy, and I've got a work term, like a work equals delta H, and I need a PV. And do I need a PV? How do I solve enthalpy when I've got a constant? And so your engineering head is already into the equation. Which means that if, in the process of writing down the answer, you've missed something useful, I can't find it. I have no idea what you've done. If you've gone off to a steam table and looked up data instead of doing an ideal gas problem, and you've just written enthalpy something or other, I don't quite know where you've gone off the rails, but also more importantly, this is not just about you and me and marking exams and marking assignments. This is about you as an engineer communicating with either your client or your boss or someone in the future because you've documented your work and then you left the company and they pick up your work to understand what you did and understand why the bridge fell down or the plane came out of the sky or the turbine blew up. You say, well, it wasn't his fault, it was science. Well, actually, no, it was his fault, I can see right here. Or we can't tell that it was his fault or her fault because I just can't see any documentation of what their assumptions were. So, assumptions here. One is given to us on a platter, steady flow. Two, you can number or letter these. I have a habit of numbering or lettering them so that when I cross something out, I can just quickly refer to, like if I cross something out and say 1, it's shorthand for saying I crossed it out because of assumption number 1. Steady flow, steady state, which is to say the states at 1 and 2 are not changing over time. 3, adiabatic. These ones were all given to us. 4, not given to us, but very, very common. I'm going to write delta KE, delta PE, approximately equal to 0. Not saying that they are 0. You could also write negligible, but I find it takes a long time to write the word negligible, and I usually don't spell it right. So kinetic energy, potential energy changes approximately equal to 0. And the last one is also a hint as to how I am going to find the properties. Ideal gas. It didn't tell me nitrogen was an ideal gas, so this is actually my assumption. If I had a nitrogen steam table with a superheated nitrogen table, I could use a table. So by saying ideal gas, this is now me telling the reader code words. Basically, I'm going to use Cp delta T. Me putting that down says I'm not going to look up a table for properties. If I need to solve anything, I'm going to use the ideal gas equation of state, PV equals RT, P little v equals RT, and Cp delta T or Cv delta T. That's what this means. Then also I need to write, we're going to find shaft work in kilowatts. That's my goal. I've got a diagram, I've got data, I've got assumptions, I've got a goal. I haven't said what equation, so using continuity, and there's different shorthands you can write down for the first law. So I can just write first law, or I could write down my SFE, my steady flow energy equation. So either of those are perfectly fine. That whiteboard now has everything to set up the beginning of my solving the problem. Maybe I'll do it over here. I think all that's going on with the system that's breaking down is me expressing to the universe that I like using whiteboards and markers and finding a way to help me out. It also gives you guys a bonus for coming to class, which is nice. So up until now, I haven't solved anything, I haven't done anything. I said I was going to use the continuity equation, so continuity is going to give me that m dot equals m dot 1 equals m dot 2. Okay, good. I've written it down. I said I was going to use it. I've written it down. I've done it. This means that if I write an m dot, I don't need to write m dot 1 or m dot 2. First law. So this is part A, part B. I haven't solved anything. I just said I was going to try. I was going to play with those rules, play with those laws, and see if I can solve it. So I haven't written down. I haven't yet written down. I'm just about to. Where entropy turns up. I have an idea. It's a compressor. It's a flow problem. Someone in lecture told me once that flow problems should have entropy. All right, so I probably see entropy somewhere coming. And it's ideal gas, so I probably won't even solve for entropy. I'll probably do something with temperatures. So I said before, I have a habit of writing down the whole. The whole equation before I begin. You don't need to, but if you do it, it's easier to keep track of what's going on. That's my whole equation. And I'm going to cross some stuff off. This guy is being crossed off because of 3. This guy and this guy are being crossed off because of 4. And so now I have shaft work equals m dot delta H. Minus Ws dot equals m dot delta H. And from here, so remember I've got m dot, so that's cool, that's great. From here, minus W dot S equals m dot, and let's make delta H into a bigger term. How can I write down delta H in an ideal gas problem?
CB?
C,
CB?
CB,
B.
P, CP what?
T.
CPT?
Oh, delta T.
Delta H. So CP delta T. This is important. CP T2 minus T1. Because 5. Because ideal gas. Writing the question on the board can't be solved without CP. So if you were solving this, either if it was an exam question, CP would have been written like at the end of the question. The way it's written there is as if you had access to a thermo textbook. And in LMS is a set of tables that includes the CP and CV data for basically every gas you'll ever deal with. So you do have all this information if you wanted to solve these problems. So up here I'm just going to write down the CP for nitrogen equals 1.039 in units, kilojoules per kilogram Kelvin. The units are important. The kilojoules part of the unit is important because sometimes they get written down in joules. Keep track of this, otherwise you'll be off by a factor of 1,000. This happens all the time. If you end up finding out that your turbine is a gigawatt engine, that's probably not good. If you find out that your turbine is a watt scale engine, it's also probably not good. So let's have a look at these terms. got this, and I've got this, and do I have my temperatures?
Yes.
Yeah. And what was I missing in the properties? What was I missing? So I've got two independent intensive properties for state.